Okay. All right, so I wanted to first off... So in the second lecture on Tuesday, we started looking at double integrals, and I attempted to do this one as an example. This is actually from your practical sheet that you'll get after the mid-semester break. This one's asking you to basically do this double integral over a simple rectangle where x goes from -1 to 1 and y goes from 0 to 2. Now, we choose to integrate with respect to x first because it's going to make our life easier. As I explained, that if I had to integrate with respect to y, there are two issues. One, that requires an integration by parts, right? And two, it's actually an integral you can't do, right? So a lot of the times when we do double integrals, sometimes, because in theory, you can do them two ways, right? But in practice, there will be certain questions that can be done one way and can't be done another. Now, when I say can't be done, I mean you can't do them. It turns out that if an integral can be done one way, it can actually be done both ways, but one way will involve functions you've never heard of, right? And that's what was happening with this one. So when I did this one the other way, right, just to show you it works. So this is the question. We basically have to integrate y e to the xy. If I integrate first with respect to y from 0 to 2, and then integrate that with respect to x from minus, which is the way I've done it, that way you can do, right? So the second line is just the integral of that, hang on, integrate that, hang on, what am I doing here? Oh, no, I'm doing this the other way around, but notice when I integrate it first by parts, I get this awful looking thing here. What do I get? I get 2 on x e to the 2x minus 1 on x squared e to the 2x plus 1 on x squared. Though the first two bits you can't do, right? Now I can do them, right? So the integral of 2 on x times e to the 2x turns out can be done. It involves something called the exponential integral, which is not a function you're familiar with. If I integrate the second bit, that's an integration by parts, again, which not one you could do, and it involves another exponent, and you notice the two exponential integrals actually cancel. And then when I do the integral the other way, I do get the same answer, right? But one way you can do, one way you can't. So being able to reverse the order of integration is important, right? So you can't sort of take this thing, well, whenever I get these questions, I'm just going to integrate first with respect to x, then with respect to y. Because I'll give you ones that can't be done, that you can't do that way. Or doing it that way will be a lot of work. So being able to reverse the order is something important. And keep in mind that when I ask you to do a double integral, like if I wrote out this one without the brackets, this is telling you a lot, This is saying that you're integrating this, x squared plus xy, x goes from 1 to 2, y goes from -1 to 1. So the actual integral actually has a lot of information built in it. The next thing I wanted to discuss was the last thing I ended up doing. Double integrals are an extension of integrals of standard integrals of a single variable. If we imagine that we're doing a double integral over the surface 1, right? And that's because if I ask you to find, say, the area, like let's say I've got a cylinder of height 1. If I ask you what is the area of the base, it's pi r squared. If I ask you for its volume, it's pi r squared times 1. Right? So numerically, they're the same thing. That means we can use double integrals to find areas between curves like we used to do with functions of a single variable. We just integrate the function 1. And I want to illustrate this with an example that you've probably the sort of thing you've probably seen before. Let's say, for example, right, we had a question where I asked you, what is the area bound by the functions y equals 6 minus x squared and y equals x? Right? And back to single variable calculus. What you would do is you identify which one's top and which one's bottom, or which one's above and below, however you want to call it. And what you would do is you would find the definite integral. You find where these intersect. It turns out these things intersect at x equals -3 and x equals 2. Right, and you would formulate the integral as the integral of x going from -3 to 2 of the top function 6 minus x squared minus the bottom function x. You would have done these problems before, yeah? Right? Right, and so basically when you do this one, that's what you're doing. Right? This is stuff you would have done before. Right? But we can actually do this as a double integral. Right? Instead of, think of it like this. Let's say I asked you to find this area in the xy plane, right, as a double integral. So what I do is I imagine the surface at z equals 1. So z now is coming out of the page. So imagine this is z is 1. There's a plane z equals 1 sitting here. The volume bound by that plane and above this region is numerically the same as the area of this region, isn't it? Because it's got height 1. Yeah? So I could formulate this problem as a double integral of 1. And the way I would do it can you see? Yeah. Right, I've got to do a double integral of 1. And what I'd imagine is that I'm going to integrate first with respect to y, then x, and y goes from the bottom bit to the top bit. And then x goes... That's the same thing. And the reason is because if I do the first inner integral, right, so remember you work from the inside out, integral of 1 with respect to y is just y, evaluated at the upper limit. And when I do this, I get right, which is exactly what you're doing here, right? The advantage of doing this as double integrals is now we have the freedom to do this 2 ways. For example, if I asked you back in single variable calculus to work out the area bound by the curves, what is it, a half y squared minus x minus 3 and y equals x minus 1, if you were going to do this with single variable calculus, this isn't pleasant, right? Because what I would have to do is I would have to split the region here and do 2 integrals. Right, and between x equals minus 3 and x equals minus 1, the top bit is the positive square root of that parabola, the bottom bit is the negative square root. And then from x equals minus 1 to 5, the top bit is the positive square root, the bottom bit is that straight line. So to do this, you would have to formulate the problem as these two integrals. Right? But that's a lot of work, right? A lot more work than's necessary, because now if I think of this instead as a double integral of the surface 1 sitting above this region, and I choose deliberately to integrate with respect to x first, then x goes from the left-hand curve to the right-hand curve, and y goes from -2 to 4. Right? So it's made my life easier. That's far easier to integrate. Right? So this is leading into double integrals over general regions. So far we've only done them over rectangles. Right? But the catch here is we can find a volume of a surface that sits above any closed region in the xy plane. Then the hard part is formulating the limits. There are two things to remember. One, that the answer is a number. Right? There's no such thing as an indefinite double integral. Right? So that means that your last iterate, which is your outer integral, those limits must be constants. Right? When you're done, you shouldn't have any x's and y's left, right? Because your answer is a number. The inner limits will be functions, and the trick is finding them. Right? And I'll show you how we do it. Oh, go away. Right? So as long as the region's closed, we can still find the volume of a surface that sits above the region, provided it's closed and provided we can work out what the bounds are as functions. Right? So by definition, a region is one which is closed, so the boundary is included, so it's nice and well defined, right? That it's a nice closed region. There's no such thing as doing this over open regions. Let's say, for example, we've got one where a region is conveniently described to be bound by two functions of x. So you've got y equals functions of x. Right? So the lower curve is some y equals g of x, the top curve is some y equals h of x. Right? We call this a type 1, and 1 here is in Roman numerals. I always mix those up, hang on. Yes, right, because triple integrals, then we use numbers 1, 2, 3, so we'll worry about that later. Right, this is a type 1, or some textbooks call it a vertically simple region, but I just call them type 1, type 2. Right, and the way we work out how we describe the region is remembering that we're going to be doing a double integral and calculating a number, which is a volume. Right, one of my sets of limits must be constants. So I imagine that y goes from the lower curve to the upper curve, and x goes from the left-hand point to the right-hand point. Imagine it's a small sweep, big sweep. Right, to sweep this region out, y goes from a small sweep from the lower curve to the top curve, so y goes from g of x to h of x. Then x is a big sweep that sweeps out the whole thing from left to right. Right? And then x goes from a to b. Right? Then a double integral over that region will be, I integrate first with respect to y from the lower curve to the upper curve, then with respect to x from my big sweep left to my big sweep right. Right? Alternatively, you could do it the other way. Imagine you've got a region that's better described as not thinking of y in terms of x, but x in terms of y. Right? Then you have x going from the left curve to the right curve, and y doing a big sweep from the bottom to the top that sweeps out the whole region. Right? This is called a region of type 2, a type 2 region, or a horizontally simple region in some books. Right? And then the integral will be this, and you first integrate with respect to x, then y. As we saw with rectangles, in theory, the order will not matter. But in practice, what will happen is that sometimes you'll get ones that can be done one way and not the other. Or one way will be a lot more work than the other. Right? This is best shown by an example. This is basically how you do it. The main thing is you must draw the region. It will almost solve all your problems. Draw the region, and I'm only going to give you bounding curves that you know, parabolas and crap like that. If it's anything more complicated, I will give you a diagram of the region. All right? All of this will make sense when we do an example. Let's think of this one. Right? Let's say I'm going to do a double integral over this region, and it's a region bound by y equals x cubed and x equals y squared. Right? Now, I'm actually going to do this by hand to show you the process. So basically, this is the question. Right? You don't have to write it, it's in there. I've asked you to find a double integral of the surface xy, where R is the region bound by y equals x cubed. Right? The first thing to do is draw it. Draw the region. Right? Doesn't have to be a work of art, especially when I'm drawing it. Right? Y equals x cubed looks something like that. X equals y squared looks something like that. Yes, I can't draw for crap. Right? But right? So it's got to be a closed region, so it's this. Right? If you have two graphs where there are multiple regions, the question will make it clear which one I want you to do. Right? I don't have to be clear here. There's only one region these two things have in common, that is closed with these two. Right? Then what I do, this is the curve y equals x cubed, or alternatively, x is y to the third. Yeah? I write all of this out even before I attack the integral. This is the curve or alternatively plus root x. The negative root x is that lower bit of that parabola that's on its side. I don't give a crap about that bit. It's not part of the question. Right? So it's got to be unique. Right? So the region you're integrating over, the functions will have inverses. Right? Unique inverses. Right? As I say, the y is minus root x is that lower bit. Now I've got to decide which way do I want to do it. If I decide, let's say I want to integrate with respect to x first. I imagine I'm sitting anywhere inside the region. Doesn't matter where it is. Right? If I'm going to integrate with respect to x first, I want x, the bounds of x going from left to right. Right? So I imagine I do a small sweep in x. So I could have this region described by x going from those curves, right, in positive x direction, of course, right? So x goes from the left-hand curve, which is y squared, to the right-hand curve, which is the positive square root of x. The right-hand curve, which is x is y to the third. So that's my small sweep. And then my big sweep is finding the extremities. Right? Now, it should be clear that these things intersect at, you get the idea, the origin and it. Right? You can find that by saying, well, when do these two curves meet? Well, you'd have y is, the first one says y squared is x to the 6, the second one is x, so you've got x equals x to the 6, right? That's x to the 6 minus x, that's x to the, don't do it in your head, x times x to the 5 minus 1, that's x equals 0, x equals 1. Right, so my big sweep in y is y goes from now the extremities, because my last sweep must be, the limits must be constants. So I could describe it like that. Or I could imagine if I'm sitting somewhere else, it shouldn't matter where you're sitting. If I want to integrate with respect to y first, I'm going to do a small sweep in y. So y goes from this curve to this curve. And then my big sweep in x goes to the extremities. Right? See, small sweep, big sweep. That's what I call them. So in this case, x goes from, y goes from this one to this one, and x my big sweep, right? Then I've now got, now I can do the integral two ways. I could either say, so, if I'm going to do x first, then y, or I could do y first, then x. And they will both, in theory, give the same answer, provided you can do the integral. Now, you're looking at these two, there isn't really a way that is jumping out that's easier, is it? I mean, the function you're integrating, x times y, that's pretty straightforward to integrate, right? I mean, yes, you've got an x to the half here, but you've got a y to the third here. They're probably about as difficult as each other, right? When I give you these questions, you know, it's useful if you've got the time to check your answer, but you don't have to do it two ways unless I specifically ask you to. But in this one, choice is yours, right? Doesn't matter which way you do it. All right, so right? So I could do it the first way. I think I've swapped them around. Yeah, you know, that's first. Well, that's the first one I did. That first, x goes from y squared to y to the third. Y going, you know, if I do that, I integrate this with respect to x. So imagine that's a constant times x. You know, when I do it by hand, I put x equals y to the third and x equals y squared, so I don't stuff it up, right? Then and you get 5 on 48 when you actually do it. Or I do it the other way. Intermediate steps are different, but the final answer must be the same. Okay? Right, and they're both about as difficult as each other. Right? The hardest part with double integrals is finding the bounds. But you do it through a process. Basically, draw a diagram. Right? Identify all of the bounding curves and write them as inverses. X in terms of y, y in terms of x. Just do it. Right? Right, and then you do small sweeps, big sweeps, and then you've got to then, from that information and the function you're integrating, the choice of which way to do it is yours. All right? And keep in mind that sometimes you'll do ones where one way is impossible. Again, it's like everything in maths. It's a skill that comes with practice. Right? And that's basically what this is saying. Okay? Now, so both calculate. The first double is a little bit easier because it doesn't involve fractional powers, but really about the same difficulty. Okay. Now, there's a couple more examples here. All right, and a couple of them I want to work through. Here we go. Let's evaluate this double integral where R is a region bound by y equals root x and y equals x cubed. Before I even think about looking at the damn integral, I draw it. Right? I find their points of intersection, and this is what it looks like. Right? Very similar to actually the region we just did. Right? And I draw all of this and figure this all out first. Right? And then I've got to decide, well, if I'm going to integrate with respect to y first, I'm going to do a small sweep in y from the lower curve to the upper curve. So y would go from x cubed to root x, and then a big sweep in x, x would go from 0 to 1. Or I could do a small sweep in x, so x goes from the left curve to the right curve. So x goes from y squared to y to the third, and y goes from 0 to 1. Right, and then from those I've got to decide which way is easier. This is another one where both ways are pretty much the same difficulty. Right? And I've done it both ways. You remember, you don't have to do it both ways unless I specifically ask you to. But being able to formulate a problem both ways, you must be able to do. Right? Once you've formulated it, it's just mechanics. Right? Just remember, the answer is a number. Your outer limits must be constants. Your inner limits are functions, and your outer limits are constants. And of course, you get the same answer. Let's have a look at this one, right? This is a classic sort of question that I will give you. Now, the way I'm going to do this one by hand, and the way I would pose this question to you in a test or something like that, is just straight out ask you, all right, and the question will be, find this. And you might think, oh, easy, off I go. What's the problem? What's the problem? Can you even get started? Because you can't integrate e to the x cubed. Right? I can, but you can't. Right? Because I'm giving you integrals that can be done. So that in theory, remember that book I showed you, that really big blue book? That's full of functions. One chapter is all the functions we're doing in this unit. Right? The other 20-something chapters are all new functions. Right? There's tons of them. Right? But you can't do this one as it stands. But also recall this simple couple of bits of functions. This is telling you a lot. Read it out in words. What this is asking you to do, integrate the surface, find the volume bound by the surface y e to the x cubed, which I do not expect you to visualise. Awful. From x over the region in the xy plane bound by x going from y on 2 to 1 as a small sweep and y going from 0 to 2 as a big sweep. Right, so the first thing to do is draw a diagram of the region, right? Because I have to swap it. I can integrate with respect to y first, that's fine. Although I don't know if that's going to help yet. Right? When you get the hang of it, you'll see what's going to happen. Right? But, because you might think, well, so what? I can integrate with respect to y. The next step I've got to integrate with respect to x, I've got the same frickin' problem. Not necessarily. When the inner limits are functions, you don't know what will happen. Right? And of course, I'm going to make sure it's doable for you. Right? But draw the region first. So we've got the basic of the line x equals y on 2, which is this. And then we've got x going from 0 to 2. And of course, when x equals 2, y equals 4. Hang on. No, y goes 0 to 2, you idiot. And x goes from x equals y on 2 to x equals 1, which is this line. Right? That's the region, because it says x goes from this curve to this curve, and y goes from this sweep to this sweep, you see? So to flip it around, so I don't want to integrate with respect to x first. So y in this case would go from this curve, which is y equals 0, to this curve, which is y equals 2x, right? And then x goes from 0 to 1, right? So this thing is the same as, and then y going from so that should be equivalent, right? Because again, you draw the region. This says x goes from here to here, small sweep, x goes from here to here, y goes at a big sweep to sweep out the whole there to there. Or alternatively, this one, y goes from there to there. And it shouldn't matter how you do it. But at least the second way, I can get started. Right? I can integrate that with respect to y, and what I hope is I get something I can then integrate with respect to x. Notice it's not immediately obvious. Some of you might spot it though. What's going to happen? You're basically going to end up with an x squared e to the x cubed. substitution. Done. Right? So if I do the first iterate, now if I integrate this, it's a half y squared. Right? Now, at the upper limit, lower limit 0, that's always nice. So 2x all squared is 4x squared. So basically you're left with that I can do. Right? So notice that I have to be very careful that the limits work when I give you these problems. Right? That you can do. Right? That's a simple substitution. Right? If you need to do the substitution steps, do it. So if I wrote this as this, what this would be, again, if you're not comfortable doing these simple substitutions in your head, do it on the side like I've shown you. Right? But it integrates to give that. Let me just 2/3 times 3x squared. Yep, that's, and I've got this going from, so 2/3 times e to the 1, which is just e minus 2 e to the 0. Right? Right, so being able to reverse the order is important. Now, as I said, you can actually do it the other way, right? But you can't, I haven't shown you how to, the reason we couldn't do it this way is essentially because I'm asking you what is, right? You can't do that one, right? Right, so this is the same problem. If I integrate y e to the x cubed first from y from 0 to 2x, I get that, right? Which is what I did by hand. I then integrate that from x is 0 to 1, I get that, right? Which I'm numerically evaluating. I'll tell you why that in a sec. Of course, you could just leave your, I'm happy with that. If I integrate this with respect to x first, that's the answer. Right, which obviously you don't understand, right? Because it involves something called the gamma function, complex numbers, gamma function, and that other one's called the incomplete gamma function. Awful thing to work with, right? Things you don't know about, right? So that's the first integral with respect to x, right? If I evaluate this from x equals 1, integrate that from x equals 1 to y on 2, I get that. Which then, even this, my computer algebra system is one of the most powerful ones, it can't do that. Right? It can't integrate that with respect to y. Right? It's one of these things are dumb. I can do that by hand. I don't want to, but I can. Right? But the computer algebra system can't. They're actually not that smart, believe it or not. What I've done here is I've asked Maple to calculate everything. Right, and then integrate it, right? So when it integrates that, I ask it to integrate that, and with a bit of rounding error, it's spitting out a complex number with a basically 0 imaginary part. But the point here is, right? It does give the same answer, as it should, right? But doing it that way, and doing that so to do that one by hand, right, because actually, and Maple can't do it. I could do it by hand. Now to do that one by hand, what would I have to do? First bit's fine, because that's all numbers. That's a linear function in y. Then it's basically a constant times y plus a constant times 1 on y squared. I can integrate that. The third bit, however, is 1 on y squared times the incomplete gamma function with y cubed as an argument. I would have to do that by parts twice and then do a complex integral to actually do it. Right? It's Right? The point I'm trying to make here is that they can be done both ways, but one way is doable, this is not, let's call this not doable, right? So being able to reverse the order is important, okay? But the main thing is, just remember this, when you give a question like this is telling you a lot, right? And being able to do these integrals both ways is important. Of course, in tests and stuff, unless I specifically ask you to, I don't want you to do them two ways, but you do need to be able to reverse. Draw the diagram. Always draw the diagram. Always find out all the bounding expressions for the bounding curves, even before you look at the integral, right? Because it might turn out one way's easy or one way's impossible, right? Then there's one more here, right? So I've got to evaluate this one. R is a region bound by the parabola x equals y squared and the line x plus y equals 2. I find where they intersect, right? So basically this, if I say this is x equals 2, you can do this several ways, of course, two equations and two unknowns. But essentially, that's what I get, right? And I draw the region, right? And I've got the bounding curves. Now, what's the problem here? If let's say I wanted to integrate with respect to y first, what's the problem? I haven't even looked at, not even looking at the integral yet, right? But if I wanted to integrate with respect to y first, if I'm sitting over here, y goes from this curve to this curve, that's minus root x to plus root x. But over here, y goes from minus root x to 2 minus x. Two double integrals. Crap. Whereas, if I integrate with respect to x first, then x goes from this, I know I haven't drawn that very well, but this is actually all one curve. That's y squared to 2 minus y. And then x as a big sweep goes from this point, sweeps out the whole, imagine you draw a big rectangle around it. Where, rectangles looks like, but you get the idea, right? So one way, I could either think of it like this, whereas there's x goes between x from 0 to 1, y goes from minus, so that's where I'm splitting the region here, and then x from 1 to 4, it looks like this, or which way is easier? The second one, obviously, because it's only going to need one integral, right? But then you've got to look at what you're integrating. Oh, that's fine, I can actually do that either way. It's not going to matter, So the order of integration can be determined by one of two things, or both. It's either what you're integrating, or the region you're integrating over, or both, right? So you need to be able to reverse the order and decide. And again, it's a skill that will come with practice, right? So if I do it the easier way, right? The algebra gets it. It's only algebra though. It's not too awful. I'm not going to give you ones that I'm not going to ask you to give you something where, unless I have stuff up, of course, where you've got to expand out, 2 minus y to the 37 or something. I'm not going to be that stupid, right? It's not too bad. Bit of algebra. Algebra's fun. All right, integrate it. Always going to have your calculator. Decimals, I don't care, right? Decimals is fine. 2 decimal places is fine. If I wanted to do it as a type 1, I'd have to do 2. And you will get the same answer, but much more work and, of course, a lot more chance of making a mistake, isn't there? Okay? All right, the main thing is draw the diagram and imagine a small sweep, big sweep. Okay? All right, so make sure you do practice these because we're going to be doing, triple integrals and things like that, and finding the regions and the bounds is a crucial skill to have. So make sure you work through these examples and the example in the lecture notes. Do them both ways as practice as long as you can actually do them both ways. All right? So in all of these examples I've shown in the lecture notes and the ones in here, they can all be done both ways although the last one's a lot of work, except for this one, because you can't integrate it. Okay? All right, make sure you do practice. Now, obviously we've got the mid-semester break, and with Easter and things like that. All right, so next week there's obviously no classes. I will have consultation as normal on Tuesday, Wednesday, Thursday from 9 till 12. So if you want to collect your test paper, or you've been, want some one-on-one help to, with the first 8 weeks of material, I will be around. It's not a holiday for us, it's only a holiday for you. Buggers. Right, we don't get it. Right, so I get Friday, Monday off, but that's it. Right, so I'll be here Tuesday, Wednesday, Thursday. Friday I have meetings, so, okay? But I'll be around 9 till 12. If you want to meet outside those times next week, just email me ahead in advance, okay? All right, enjoy your Easter long weekend, everyone, and I'll see you when you all come back.